today we're gonna learn about
Math, 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 math.
mathematics is a science that deals with the logic of shapes, quantity, and arrangement. It is considered as the building blocks for everything in our daily lives since math is all around us, including art, architecture, engineering, money, and even sports. Aristotle defined mathematics as the science of quantity, and on the other hand, Galileo defined mathematics as the language with which God has written the universe. And next, we will learn about the history of mathematics. So, stay tuned.
Good day everyone, this is Joseph Renier P. Abad from BSMA 11 and we will now be discussing the history of mathematics, starting with the prehistoric mathematics. During the prehistoric times, our ancestors already knew the difference of having one wood and two woods, but of course it is only based on their instincts, since the idea of numbers was not yet present during that time. It took many ages for the invention of symbols or words or even the concept of numbers itself to come. The earliest evidences of mankind thinking about numbers were probably the notched bones in Africa dating back to 35,000 to 20,000 years ago. These notched bones were used to keep track of regular occurrences such as the phases of the moon, the seasons, and etc. So with this, it is actually believed that mathematics really started or was really developed during the Sumerian or Babylonian period. Sumerian mathematics initially started as a response to bureaucratic needs when the Sumerians developed agriculture as early as 6th millennium BCE. So back then, mathematics was used for the measurement of plots of land, for the computation of the taxes of the individuals, and etc. In addition, the Sumerians and the Babylonians also needed to describe large numbers as they attempted to chart the course of the night sky while developing their lunar calendar. The Sumerians and the Babylonians were also the first people who assigned symbols to groups of objects in an attempt to make describing large numbers easier. As early as the 4th millennium BCE, they used a small clay in representing 1, a clay ball for representing 10, and a large clay cone for representing 60 or 60. However, over the course of the 3rd millennium BCE, these symbols or these objects were replaced by cuneiform equivalents so that the numbers could then be written with the same stylus as with the texts. The Sumerian and the Babylonian mathematics was actually based on a sexagesimal or base 60 numeric system. They also have a true place value system wherein numbers written in the left column represent much larger values, just like with our modern decimal system. The Babylonians were also the ones who developed a circular symbol for the number 0, although 0 is more of a placeholder than a number on its own right. Later Babylonian tablets dating from 18,000 to 16,000 BCE covered topics such as algebra, quadratic and linear equations, and many more. And it is actually believed that the idea of square numbers and quadratic equations arose in the context of measurement of lands. There is also this famous and controversial clay tablet known as the Plimpton 322 clay tablet, which is believed to date from around 18,000 BCE. And the Plimpton 322 clay tablet suggests that the Babylonians may well have known the secrets of the right-angled triangles many centuries before the Greek Pythagoras. The clay tablet appears to list 15 perfect Pythagorean triangles with whole number sides, although many people believe that these triangles were just merely academic exercises and not deliberate manifestations of the Pythagorean triples. So that is it for the prehistoric and the Sumerian or Babylonian mathematics. Now, Mark Christian Aguilar will be discussing Egyptian mathematics.
The Egyptian mathematics. As early as 6000 BCE, the early Egyptians settled along the Nile Valley and began to record the patterns of the time periods and seasons for agricultural and religious purposes. Very early in Egyptian history, the pharaoh's auditors used their body parts to measure things. Example, a palm was the width of the hand. A cubit is the measurement from your elbow up to your fingertips. This is the cubit. And they also use this to measure buildings and lands. And also, they develop a decimal numeric system based on our 10 fingers. The Moscow Papyrus, which dates from Egyptian Middle Kingdom between 2000 and 1800 BCE, is the oldest mathematician text discovered in ancient Egypt. Who invented or started math in Egypt? The Rhind Papyrus in the 19th century, dated from 1650 BCE, is discovered by an antiquarian and archaeologist named Alexander Henry Rhind. It is an instruction manual of arithmetic and geometry with explicit demonstration on how multiplication and division were used at that times. It also demonstrates mathematical knowledge such as unit and fractions, and also other complex problems in mathematics. And now let's talk about ancient Egyptian number system. It is believed that ancient Egypt or Egyptians introduced the fully developed base 10 numeral system as early as 2700 BCE or probably much earlier. This number system is called the Egyptian numeral hieroglyphs or the Egyptian hieroglyphic numerals. These are written numbers of stroke or written numbers used as stroke for units, or these are the symbol that equals to a certain amount. Example, a symbol of a heel bone that equals to a amount of 10. A symbol of a coil of rope for 100, a lotus flower, a lotus plant for 1000, and many more other symbols for higher power of 10, up to million. However, there were no concept of place value, so larger the numbers were rather unwieldy or complex. And now, let's show you an ancient Egyptian method of multiplication. So this is what we call the Egyptian doubling method of multiplication or in multiplication. So how it works? So it is achieved by a process of repeated doubling of the number to be multiplied from one side to the other side. So let's see. So ayan po, nakikita nyo sa picture. The problem was listed sa pinaka-top. Yan, sa pinaka-top po nakalagay, and it is listed horizontally. Left is the multiplier and the right is the multiplicand. So the next is consists of two columns. Meron po siya sa left and to the right side. So let's talk about first the left side. Sa left side po, or sa multiplier side, magsisimula siya sa 1. Kapag dinouble mo po is 1 times 2 is equals 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So, paano malalaman kung titigil ka na dun sa side ng column na yon? So, kung makikita nyo po dyan, ang multiplier is 19 at tumigil sa 16. So, malalaman nyo po na titigil na kapag yung next number or sa next na multiplier is mag-exceed na po dun sa pinaka base dun sa problem. So, dyan po is nag-stop siya sa 16 dahil ang sunod po ng 16 times 2 is 32. So, kapag sinama po yung 32 is lagpas na po siya sa 19. So, hindi na po isasama yan. So, next is to the right side. Sa right column naman po tayo. Kung makikita nyo po, nag-start siya sa pinaka-base. Yung pinaka-base niya po is yung multiplicand. So, 54. Ngayon, Same process lang po. 54 times 2 is 108. Tapos susundan lang times 2, 216 times 2, 432. And last is 164. So, paano mo naman malalaman kung titigil ka na sa right column or sa kabilang side? Bale, ang mangyayari po, sasabayan nyo lang yung pinaka-last na number sa left. Kung ano po yung papantay dun sa left side, di ba 16 po? Kung ano yung papantay dun, then dun din titigil yung sa right side. So, next process naman po is ipag-a-add yung i-add po yung nasa left side, yung nag-i-start sa number 1. So, paano yung mangyayari? So, mangyayari, dun po sa listed numbers from top to bottom, hindi kasama yung 19, ang nangyayari, hanapin nyo po yung number or combination of number that will sums up to the number 19. So, pag pinag-plus po natin yung 1, yung 2, and yung 16, it is equals to 19. So, ngayon, in-circle po natin yon dahil sila po yung mga number that will result to number 19. So, ngayon, after next process is ngayon yung mga naka-circle na number, titingnan mo yung katapat nila. Then, yung katapat nila, ipagpa-plus natin, isasum natin yung mga katapat ng mga nakabilog. Then, ayun yung magiging sagot ng multiplication. So, tingnan po natin. So, dito, nakabilog yung number 1. And katapat ng number 1 is 54. Next, number 2, nakabilog. Then, katapat ng number 2 is 108. And pinaka-last is yung 16 yung nakabilog. So, yung nakabilog lang po yung i-focus natin. So, ang katapat ng nakabilog is yung 864, which is also the last number and then or in the right side or in the right column. So, ngayon yung katapat po ng mga nakabilog, ipapa-plus po natin sila and the answer will also be the answer or the product in the problem. So, kapag pinag-plus po natin yung 54, yung 108, and yung 864, it is 1026. So, kapag pinag-times nyo po yung 19 and 54, the answer is also 1026. So, ganun po nila kinukuha dati yung product or ito po yung doubling method ng mga Egyptian noon kumpara sa system of multiplication natin ngayon. So, ayan. So, for the last question, why did ancient Egyptians use mathematics? So, the Egyptians were very practical when it came to mathematics because it is required for them in trading to be able to deal with fractions. So, one of the earliest invention in ancient Egyptian was the use of mathematics for variety of purposes, such as calculating taxes to be paid, counting money, calculating land areas, and even in cooking. So, these taxes were paid with labor, goods produced by farmers or goods sold by traders. Egyptians were really good in mathematics, and the pyramids themselves were the evidence of Egyptians' mathematics sophistication. And that's all for Egyptian mathematics.
Kalimera, good day. This is Ariela May Andrada, and today we will try to turn back time as we reminisce and enter the wondrous history of Greek mathematics. Greek mathematics refers to mathematics texts written during and ideas stemming from the Archaic through the Hellenistic periods, extant from the 7th century BC to the 4th century AD. Around the shores of the Eastern Mediterranean, Greek mathematicians lived in cities spread over the entire Eastern Mediterranean from Italy to North Africa, but were united by the Greek culture and the Greek language. The word mathematics itself derives from the ancient Greek mathema, means subject of instruction. The study of mathematics for its own sake and the use of generalized mathematical theories and proofs is an important difference between Greek mathematics and those of preceding civilizations. The origin of Greek mathematics is not well documented. The earliest advanced civilizations in Greece and in Europe were the Minoan and the later
Mycenaean civilizations, both of which flourished during the second millennium BC. While these civilizations possessed writing and were capable of advanced engineering, including four-story palaces with drainage and beehive tombs, they left behind no mathematical documents. Though no direct evidence is available, it is generally thought that the neighboring Babylonian and Egyptian civilizations had an influence on the younger Greek tradition. Unlike the flourishing of Greek literature in the span of 800 to 600 BC, very little is known about Greek mathematics in this early period, nearly all of which was passed down through later authors beginning in the mid-4th century BC. Their solutions provided the fundamental mathematical building blocks that all future mathematicians and scientists would build up right upon to the present day. As the Greek Empire began to spread its sphere of influence into Asia Minor, Mesopotamia, and beyond, the Greeks were smart enough to adopt useful elements from the societies they conquered. This was as true of their mathematics as anything else, and they adopted elements of mathematics from both the Babylonians and the Egyptians. But they soon started to make important contributions in their own right, and for the first time, we can acknowledge contributions by individuals. The ancient Greek numeral system, known as Attic or Herodianic numerals, was fully developed by about 450 BCE and in regular use possibly as early as the 7th century BCE. It was a base 10 system similar to the earlier Egyptian one, with symbols for 1, 5, 10, 50, 100, 500, and 1000, repeated as many times needed to represent the desired number. But most of Greek mathematics was based on geometry. Thales, one of the 7 sages of ancient Greek, who lived on the Iowan coast of Asia Minor in the first half of the 6th century BCE, is usually considered to have been the first to lay down guidelines for the abstract development of geometry. To some extent, however, the legend of the 6th century BCE mathematician Pythagoras of Samos has become synonymous with the birth of Greek mathematics. Indeed, he is believed to have coined both the words philosophy and mathematics. Pythagoras was perhaps the first to realize that a complete system of mathematics could be constructed, where geometric elements corresponded with numbers. Hippocrates of Chios was one such Greek mathematician who applied himself to these problems during the 5th century BCE. His influential book, The Elements, dating to around 440 BCE, was the first compilation of the elements of geometry, and his work was an important source for Euclid's later work. It was the Greek who first grappled with the idea of infinity, such as described in the well-known paradoxes attributed to the philosopher Zeno of Elea in the 5th century BCE. The most famous of his paradoxes is that Achilles and the tortoise, which describes a theoretical race between Achilles and the tortoise. Democritus, most famous for his prescient ideas about all matter being composed of tiny atoms, was also a pioneer of mathematics and geometry in the 5th to 4th century BCE, and he produced works with titles like On Numbers, On Geometrics, On Tangencies, On Mapping, and On Irrationals, although these works have not survived. Plato's student Eudoxus of Cnidus is usually credited with the first implementation of the method of exhaustion, later developed by Archimedes, an early method of integration by successive approximation which he used for the calculation of the volume of the pyramid in cone. Perhaps the most important single contribution of the Greeks, though, and Pythagoras, Plato, and Aristotle were all influential in this respect, was the idea of proof and the deductive method of using logical steps to prove or disprove theorems, from initial assumed axioms. Older cultures like the Egyptians and the Babylonians had relied on inductive reasoning, that is, using repeated observations to establish rules of thumb. It is this concept of proof that gives mathematics its power and ensures that proven theories are as true today as they were 2,000 years ago, and which laid the foundations for the systematic approach to mathematics of Euclid and those who came after him. And for the finale, a little fun fact. From the viewpoint of Greek mathematics, it is best to distinguish between the two periods. The classical period from the 600 BC to 300 BC and the Alexandrian or Hellenistic period from 300 BC to 300 AD. Indeed, from about 350 BC, the center of mathematics moved from Athens to Alexandria in Egypt, the city built by Alexander the Great. It remained the center of mathematics for a millennium until the library was sacked by the Muslims in about 700 AD. In actual fact, our direct knowledge of Greek mathematics is less reliable than that of the older Egyptian and Babylonian mathematics because none of the original manuscripts are extant. There are only two sources. First, Byzantine Greek codices, written 500 to 1500 years after the Greek works were composed, and second, Arabic translations of Greek words and Latin translations of the Arabic versions. Moreover, we do not know yet even if these works were made from the originals. For example, Heron made a number of changes in Euclid's elements, adding new cases. Likewise for Theon of Alexandria. And that ends my report. Sas Evaristo, thank you.
So after discussing about the Greek mathematics, we will now proceed to the Hellenistic period with Alexander's conquest of the Eastern Mediterranean, including Egypt, Mesopotamia, and the Iranian plateau. Greek became the language of scholarship throughout the Hellenistic world, and the Greek merged with the Egyptian and Babylonian mathematics to form the Hellenistic mathematics. And it plays an important role in the history of mathematics. So without further ado, we will now deepen our understanding about the history of mathematics, specifically in the Hellenistic period. Hellenistic mathematics began in the 3rd century BCE as Alexander the Great conquered nearby countries. This marks the beginning of a new era known as Hellenistic Age. Along its birth, mathematical breakthroughs were also the beginning to be made. During this period, Alexandria in Egypt was built, which became the center of learning under the rule of Ptolemies, a companion of Alexander the Great. Among the best known and most influential mathematicians who studied and taught at Alexandria were Euclid, Archimedes, Eratosthenes, Heron, Menelaus, and Diophantus. During the late 4th and early 3rd century BCE, Euclid was the great chronicler of the mathematics of the time, one of the most influential teachers in history. He virtually invented classical Euclidean, or geometry as we know it. Archimedes spent most of his life in Syracuse, Sicily, but also studied for a while in Alexandria. He is perhaps best known as an engineer and inventor, but in the light of recent discoveries, he is now considered one of the greatest pure mathematicians of all time. Eratosthenes of Alexandria was a near contemporary of Archimedes in the 3rd century BCE. A mathematician, astronomer, and geographer, he devised the first system of latitude and longitude and calculated the circumference of the Earth to a remarkable degree of accuracy. As a mathematician, his greatest legacy is the sieve of Eratosthenes, algorithm for identifying prime numbers. The sieve of Eratosthenes is a simple algorithm to identify all the prime numbers up to any value. Ignoring one The first prime is 2, so start by marking off all the other numbers which are divisible by 2. The next prime is 3, so mark off all the other numbers which are divisible by 3. The next prime is 5 and then 7. Proceed in the same way. The numbers remaining in white are prime numbers, as are the 2, 3, 5, and 7.
It is not known exactly when the Great Library of Alexandria burnt down, but Alexandria remained an important intellectual center for some centuries. In the 1st century BCE, Hero was another great Alexandrian inventor, best known in mathematical circles for Heronian triangles with integer sides and integer area. Heron's formula for finding the area of a triangle from its side lengths, and Heron's method for iteratively computing a square root. He was also the first mathematician to confront at least the idea of square root of -1, although he had no idea how to treat it, something which had to wait for Tartaglia and Cardano in the 16th century.
Menelaus of Alexandria, who lived in the 1st to 2nd century CE, was the first to recognize geodesics on a curved surface as the natural analogues of straight lines on a flat plane. His book Spherica dealt with the geometry of the sphere and its application in astronomical measurements and calculations, and introduced the concept of spherical triangle, a figure form of 3 great circle arcs which he named trilaterals.
In the 3rd century CE, Diophantus of Alexandria was the first to recognize fractions as numbers and is considered an early innovator in the field of what would later become known as algebra. He applied himself to some quite complex algebraic problems, including what is now known as Diophantine analysis, which deals with finding integer solutions to kind of problems that lead to equations in several unknowns. Diophantus Arithmetica, a collection of problems giving numerical solutions of both determinate and indeterminate equations, was the most prominent work on algebra in all Greek mathematics, and his problems exercised the minds of many of the world's best mathematicians for much of the next 2 millennia. But Alexandria was not the only center of learning in the Hellenistic Greek Empire. Mention should also be made of Apollonius of Perga, a city in modern-day southern Turkey, whose late 3rd century BCE work on geometry, and in particular on conics and conic sections, was very influential on later European mathematicians. It was Apollonius who gave the ellipse, the parabola, and the hyperbola the names by which we know them, and showed how they could be derived from different sections through a cone. Hipparchus, who was also from Hellenistic Anatolia and who lived in the 2nd century BCE, was perhaps the greatest of all ancient astronomers. He revived the use of arithmetic techniques first developed by the Chaldeans and Babylonians, and is usually credited with the beginning of trigonometry. He calculated with remarkable accuracy for the time the distance of the moon from the earth by measuring the different parts of the moon visible at different locations and calculating the distance using the properties of triangles. He went on to create the first table of chords, side lengths corresponding to different angles of a triangle. By the time of the great Alexandrian astronomer Ptolemy in the 2nd century CE, however, Greek mastery of numerical procedures had progressed to the point where Ptolemy was able to include in his Almagest a table of trigonometric chords in a circle for steps of 1/4 degrees, which, although expressed sexagesimally in the Babylonian style, is accurate to about 5 decimal places. By the middle of the 1st century BCE, and therefore, however, the Romans had tightened their grip on the old Greek Empire. The Romans had no use for pure mathematics, only for its practical applications. The Christian regime that followed it even less so. The final blow to the Hellenistic mathematical heritage at Alexandria might be seen in the figure of Hypatia, the first recorded female mathematician, and a renowned teacher who had written some respect commentaries on Diophantus and Apollonius. She was drummed to her death by a Christian mob in 415 CE.
Hi!
Hello, my name is Balsar Jr. Asbertillo at ang tatalakayin natin ngayon ay ang Roman Mathematics, Numerals, and Arithmetic. Ang Roman numerals daw ay originated, as the name might suggest, in ancient Rome. There are 7 basic symbols of Roman numerals. Yung I is equal to 1, yung B is equals to 5, yung X is equal to 10, yung L is equal to 50, yung C is equal to 100, yung D is equals to 500, at ang huli naman, yung M is equals to 1,000. The first usage of these symbols began showing between 900 to 800 before Common Era. How do Roman numerals work? A symbol placed after another of equal or greater value adds its value. A symbol placed before one of greater value subtracts its value. A bar placed over a number multiplies its value by 1,000. Ang example naman based doon sa huling statement ay kapag may bar sa itaas ng Roman numeral symbol, ito ay nag-i-indicate na minultiply ito sa 1,000. Oh my God! Wow! Roman numerals are well known today and were the dominant number system for trading and administration in the most part of Europe for the best of millennium. It was a decimal system but not directly positional and did not include a zero, so that for arithmetic and mathematical purposes, it was a clumsy and inefficient system. Is it still important to learn Roman numerals? Despite the impracticality of using Roman numerals for mathematical calculations, which led to the widespread use of the Hindu-Arabic numeral system we know today, some people do still argue for the importance of teaching Roman numerals in schools. Proponents believe that Roman numerals have enduring cultural relevance, as seen in their continued use in sporting event titles and book chapters. Alam niyo ba na naging usap-usapan ang Disney Princess maternity photoshoot ni Zainab dahil isa sa mga larawan nito ay nakaagaw atensyon ang isang orasan na ganito ang pagkakasulat sa number 4. At alam niyo ba na hindi ito mali?
Paano masabi?
Dahil sa katunayan, noong unang panahon, ang mga Romano ay sumasamba sa nagngangalang Jupiter, na ang pagkakasulat ay I, B, P, I, T, T, E, R sa Latin. Kung kaya't some clockmakers are hesitant to put part of the god's name on a sundial or in accounting books. Yung 4 na I became the prepared representation of 4. At sa ngayong panahon, some clockmakers ay nagstick pa rin sa 4 na I just for the sake of tradition.
Thank you!
Ngayon, natapos na natin i-discuss ang Roman Mathematics, Numerals, and Arithmetic. Ngayon, dadako naman tayo kay Jessica May Briones para i-discuss ang Mayan Mathematics.
Good day, my name is Jessica May Briones, and today I'm going to discuss the contributions of Mayan civilization in the history of mathematics. Ancient Mayan civilization are best known as the classical civilization of Mesoamerica, which is found in the Istthmus of the Central America and in the modern day southern Mexico. The Mayan civilization was believed to emerge in 2600 BC and through the 9th century AD, in the year of the Lord, collapsed due to mysterious decline and abandonment of its own civilization. And yes, Mayans still do exist up to this day, but they are spread throughout Southern America and Mexico. Mayans were known to be great mathematicians because they were able to calculate big numbers at an early age of mathematics. According to my research in the history of mathematics, the Mayan civilization have three great contributions. The first one is the Mayan numerical system, the second one is the Mayan calendar, and the last is the concept of zeros. Now, let's go to the first contribution of Mayan in the history of mathematics. Mayans have created an accurate but sophisticated number system, which is called vigesimal number system, or the so-called base 20. Vigesimal number system is a series of symbols that represent the certain numbers for their calculations. Here are some examples of vigesimal number system. Now, let's move on to the second contribution. With the utilization of the number system they have created, they were able to calculate the Mayan calendar. Mayans were able to create two kinds of calendar based on their calculation of time and date. First, calendar is the ritual calendar called Tzolk'in, composed of 260 days in a year and 20 days in a month. The second was a civil calendar called Ha'ab, which consisted of 365 days, which was closest calculation of days in a year among their time. Did you know that Mayans were the ones who calculated that the world will end in 2012? According to the Mayan calendar, the world will end on December 21, 2012. Thankfully, it did not happen, but the fact that Mayans were able to calculate their calendar up to 2012 is very advanced for their time. Now, let's go to the last contribution, which is the calculation of zeros. Mayans were one of the civilizations whom developed zero as a placeholder around AD 350. They used it to denote a placeholder in their elaborate calendar system. With the use of this so-called Mayan zero, they were able to sum up to hundreds of millions. And that sums up my part in the history of mathematics. Again, this is Jessica May Briones. Thank you for watching.
Why was math needed in ancient China? Because it needed to control flood-prone rivers in China such as the Yangtze and Yellow rivers. The construction of dams and canals inspired mathematical calculation motivated by the problems of the calendar, trade, land, measurement, architecture, government records, and taxes. It also needs to make calculations for constructing the calendar and predicting the positions of the heavenly bodies. So here's a brief outline of the history of Chinese mathematics. First is the numerical notation, arithmetical computations, and counting rods. So the traditional decimal notation, one symbol for each of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, hundreds, thousands, and 10,000s. For example, is 2034 will be written with symbols for 2, 1000, 3, 10, 4, meaning 2 times 1000 plus 3 times 10 plus 4. So goes back to origins of Chinese writing. So for calculations, it performed using small bamboo counting rods. So the positions of the rods gave a decimal place value system. Also written for long-term records. 0 digit was a space, arranged left to right like Arabic numerals. So back to 400 BCE or earlier. So for addition, the counting rods for the two numbers placed down one number above the other. The digits added or merged left to right with carries where needed. So the subtraction is similar. So for multiplication, the multiplication table to 9 times 9 memorize. So for long multiplication similar to ours with advantages due to physical rods. So for long division analogous to current algorithms but closer to Gaussian method. Second is the Zobis-Swanson, the arithmetical classic of the Genomon and the circular paths of heaven. 100 BCE to 100 CE. It describes one of the theories of the heavens, early Han Dynasty 206 BCE to 220 CE, or earlier, book burning of 213 BCE. It states and uses the Pythagorean theorem for surveying, astronomy, etc. Proof of the Pythagorean theorem. The calculations including the common fractions. So the third one is the 9 chapters on the mathematical art, Zhu Zong Xuanshu, 100 BCE to 50 CE. It collects the mathematics to beginning of Han Dynasty. 246 problems in 9 chapters. The longest surviving and most influential Chinese math book. Many commentaries. So the chapter 1, it is about the field measurement, systematic discussion of algorithms using counting rods for common fractions, including algorithm for GCD, LCM, areas of plane figures, square, rectangle, triangle, trapezoid, circle, circle segment, sphere, segment, annulus. Some are accurate, some are approximations. So for chapters 2, 3, 6 on proportions, serials, proportional distribution, vertices. So for chapter 4, it's all about the width, given area or volume. Find sides. It describes usual algorithm for square and cube roots, but takes advantage of computations with counting rods. So for chapter 5, it's all about the construction consultations. Volumes of cube, rectangular parallel, prism frustums, pyramid, triangular pyramid, tetrahedron, cylinder, cone, and conic frustum. Sphere. Some are approximations only and some use pi. So for chapter 7, it's all about the excess and division, false position and double false position. And for chapter 8, rectangular arrays, it gives elimination algorithm for solving systems of 3 or more simultaneous linear equations. It involves use of negative numbers, red for positive numbers and black for negative numbers. So the rules for signed numbers. The chapter 9, right triangles, applications of Pythagorean theorem and similar triangles. Solves for quadratic equations with modification of square root algorithm. Only equations of the form x squared plus ax equals b, with a and b positive. The fourth one is Sun Tzu, 250 CE. He wrote his mathematical manual. It includes the Chinese remainder problem, or the problem of the master's son. It finds and so that upon division by 3, you get a remainder of 2. Upon division by 5, you get a remainder of 3. And upon division by 7, you get a remainder of 2. His solution: take 140, 63, 30, add to get 233, subtract 210 to get 23. For the fifth one is Liu Wei, 263 CE. It's all about the commentary on the 9 chapters approximates pi by approximating circles, polygons, doubling the number of sides to get a better approximations. So from 96 and 192 sided polygons, he approximates pi as 3.141014 and suggested 3.14 as a practical approximations. It states principle of exhaustion for circles. It also suggests Cavalieri's principle to find accurate volume of cylinder. Haidao Zhuanjing, Sea of Island Mathematical Manual. It originally appendix to commentary on chapter 9 of the 9 chapters. It includes 9 surveying problems involving indirect observations. So for number 6, Zhang Guijian, 450 BCE, wrote his mathematical manual. It includes the formula for summing an arithmetic sequence. It also an undetermined system of 2 linear equations in 3 unknowns. The 100 poles problem. For number 7, Zhu Zhongqi, 429 to 500, an astronomer, mathematician, and engineer. He collected together earlier astronomical writings. He made his own astronomical observation, recommended new calendar. He also determined pi to 7 digits, 3.14, 15, 92, 6. Recommended use 355 over 113 for close approximation and 22 over 7 for rough approximation. With further carried out, Liu Wei's suggestion for volume of sphere to get accurate formula for a volume of a sphere. For number 8, Liu Zhou, 544 to 610, an astronomer, introduced quadratic interpolation, the second order difference method. And number 9, Wang Xiaotong, 625, a mathematician and astronomer, wrote Shugu Zhuanjing, a continuation of ancient mathematics of 22 problems. Solve cubic equations by generalization of algorithm for cube root. For number 10, translations of Indian mathematical works by 600 CE, 3 works, Sin's Laws and Levencita, Indian, an astronomer working at State Observatory, translated 2 more texts, one of which described angle measurement 360 degrees and a table of signs for angles from 0 to 90 degrees in 24 steps, 3 and 3/4 degree increments. Hindu decimal numerals also introduced but not adopted. For number 11, Yixing, 683 to 727, an tangent table. For number 12, Jiashan, 1050, the written work clause, streamlined extraction of square and cube roots, extended method to higher degree roots using binomial coefficients. Number 13, Qinjue Shao, 1202 to 1261. Xu Shu Jiuzheng, a mathematical treatise in 9 sections. 81 problems of applied math similar to 9 chapters, solution of some higher degree up to 10 equations, a systematic treatment of indeterminate simultaneous linear congruences, Chinese remainder theorem, Euclidean algorithm for GCD. For number 14, Li Qi, aka Liye, 1192 to 1279. The Seyuan Haijing, C mirror of circle measurements, 12 chapters, 170 problems on right triangles and circles inscribed within or circumscribed about them. Yigu Yanduan, 2 steps in computation. Geometric problems solved by algebra. 15. Yang Wei, 1261 to 1275. He wrote several books, explains Jiu Shan's method for solving higher degree root extractions, magic squares of order up to true 10. Number 16, Yu Shujing, 1231 to 1316. Xu Shili works and days calendar. Higher order differences, especially higher order interpolation. Lastly, for number 17, Zhu Qiji, 1280 to 1303, Suan Shu Shimeng, Introduction to Mathematical Studies, and Xiwan Yuchan, Precious Mirror of the Four Elements, solved some higher degree polynomial equations in several unknowns. Some finite series including 1, the sum of n squared, and 2, the sum of n close parenthesis n plus 1 and close parenthesis n plus 2 divided by 6, discusses binomial coefficients and also uses 0 digit. And that's all. Thank you.
Ancient mathematics give a huge insight into the history of mathematics. Some of advanced mathematical discoveries were made at a very early time in India. One of these is the decimal place value number system. Like the Chinese, the Indians early discovered the benefits of a decimal place value number system and were certainly using it before about the 3rd century CE. They refined and perfected the system, particularly the written representation of the numerals, creating the ancestor of the 9 numerals that we use across the world today, that's sometimes considered one of the greatest intellectual innovations of all time. The Indians were also responsible for another hugely important development in mathematics, which is the earliest record usage of a circle character for the number 0. But the brilliant conceptual leap to include 0 as a number in its own right, rather than merely as a placeholder, a blank, or an empty space within a number, as it had been treated until that time, is usually credited to the 7th century Indian mathematics Brahmagupta, or possible another Indian Bhaskara I, even though it may well have been in practical use for centuries before that. On the other hand, Sanskrit, the classical language of India and the medium for its pre-modern mathematical texts, maintained a strictly oral literary tradition for many centuries. The earliest surviving Sanskrit references to a mathematical subject are some number words in the Vedas, ancient texts that were passed down by recitation and memorization. For example, as the name of successive power of 10, well beyond the 1,000 and 10,000 familiar to others ancient culture. In Golden Age, Indian mathematicians made fundamental advances in the theory of trigonometry, a method of linking geometry and numbers first developed by the Greeks. They use ideas like the sine, cosine, and tangent function, which relate the angles of a triangle to the relative lengths of its sides, to survey the
the land around them, navigate the sea, and even chart the heavens. Indian astronomers used trigonometry to calculate the relative distance between the Earth and the Moon.
So, hi guys, today we're discussing about the topic of the history of Islamic and medieval mathematics. So, yun nga, pag-uusapan natin kung ano nga yung mga nakaraan ng mathematics ng Islam at ng mga tao noong medieval period. So, unahin nga natin yung mathematics sa Islam. So, ang Islamic Empire ay binubuo ng Persia, Middle East, Central Asia, North Africa, Iberia, and some parts of India from the 8th century. So dito nga, nagkaroon ng significant contribution yung Islamic Empire sa mathematics and science. Kasi nagawa nilang paghaluin yung mathematical knowledge and developments ng Greece and India. So ano nga ba yung significant creation ng mga Islam or ng Islamic? So dito nga, kung mapapansin natin yung architecture nila, sobrang fine ng design. Kasi dito, tinuturing nilang isang art ang architecture. So pupasok na rin dito na ang mathematics para sa kanila ay isang art. At dito nga, nabuo nila yung mga iba't ibang forms ng symmetrical shapes and two-dimensional surface. So aware naman tayo na sinusunod ng mga Islam ang Quran, which is ito nga yung Bible nila. So malaking impact ito dahil yung Quran, ini-encourage din yung mga Islam to accumulate the knowledge about the science and mathematics. So dito na nga nag-umpisa yung Golden Age of Islamic Science and Mathematics. Sa sobrang improve or sa sobrang lago ng industry nila about sa mathematics and science, naapektuhan din nila, na-influensyahan din nila yung medieval period which is nasa Europe. So ito nga, 9th to 15th century. Dito nga rin nabuo yung House of Wisdom in Baghdad around 810 and work started almost immediately, transferring the Greek and Indian mathematical astronomy work into Arabic. So pag-uusapan naman natin yung mga outstanding mathematicians na sumikat noon sa Islamic period. So ito nga, one of the outstanding Persian mathematician is Muhammad al-Khwarizmi. Was an early director of the House of the Wisdom in the 9th century and one of the greatest of early Muslims mathematicians. Perhaps al-Khwarizmi's most important contribution to mathematics was his strong advocacy to Hindu numerical system. Yung Hindu numerical system, ito nga yung 1 to 9 na numbers na ginagamit natin sa pang-araw-araw natin, pati yung 0 included din dito. Which he recognized as having the power and efficiency needed to revolutionize Islamic and later Western mathematics, and which was soon adopted by the entire Islamic world and later by Europe as well. One of the most important contributions of al-Khwarizmi is algebra, and he introduced the fundamental algebraic methods of reduction and balancing, and provide an exhaustive account of solving polynomial equation up to the second degree. In this way, he helped create a powerful abstract mathematician language, still used across the world today, and allowed a much more general way of analyzing problems more than just the specific problems previously considered by the Indians and Chinese. So, hindi nga lang si Khwarizmi yung sumikat. Nandito rin yung 10th century Persian mathematician na si Muhammad al-Karaji, which is who worked to extend algebra still further. So, dito nga in-improve niya yung naunang gawa ni Khwarizmi. Tapos, in-improve niya pa yung algebra. Ito nga, papaliwanag ko sa inyo. Freeing it from geometrical heritage and introduced the theory of algebraic calculus. Al-Karaji was the first to use the method of proof by mathematical induction to prove his results by proving that the first statement in an infinite sequence of the statement is true, then providing that if any one the statement is the sequence is true, then so is the next one. Another of the most notable 13th century Persian astronomer, scientist, and mathematician was Nasir al-Din al-Tusi. Was perhaps the first to treat trigonometry as a separate mathematical discipline, distinct from the astronomy, building on earlier work by Greek mathematicians such as Menelaus of Alexandria and Indian work to sine function. He gave the first extensive exposition of spherical trigonometry, including listing the 6 distinct cases of right triangles in spherical trigonometry. One of his major mathematical contributions was the formulation of the famous law of sines for the plane triangles. Although the sine law for spherical triangles had been discovered earlier by the 10th century Persian Abul Wafa Buzjani and the Abu Nasir Mansur. So hindi nga lang sila, meron pang iba. Ito nga sila. Ito nga, yung other medieval Muslim mathematicians worthy of note include the 10th century Arab mathematician Abul Hasan al-Uqlidisi, who wrote the earliest surviving text showing the positional use of the Arabic numerical and particular use of the decimal and fraction. Andito din si 11th century Persian Ibn al-Haytham, also known as Al-Hazen, who is in addition to his groundbreaking works on optics and physics, established the beginnings of the link between algebra and geometry. So, punta naman tayo sa mathematics in medieval period. During the centuries in which the Chinese, Indian, and Islamic mathematician had been in the ascendancy, Europe had fallen into the Dark Age, in which science, mathematics, and almost all intellectuals endeavors stagnated. So, bakit nga ba? Ba't nga ba na-fall sa Dark Age yung Europe? Dito nga kasi mas nag-focus yung Europe sa pagpapalawak ng relihiyon nila, which is ito nga yung Catholic. So, dito nga mas pinagtuunan din nila ng pansin yung philosophy about sa human life, ganun. Dito nga mas nagtuunan pa talaga nila ng pansin yung mga katanungan na bubuo sa mga tao. Sa halimbawa nga nito, yung how many angels can stand on the point of a needle, which is parang useless naman para sa atin, di ba? Pero para sa nila kasi philosophy, which is may malalim na dahilan. So, ito nga, even though na pumasok nga sa Dark Age in Europe, mayroon pa naman din kahit papaano mga tao na still nag-study ng mathematics. Ito nga, isa nga dito ay si Boethius. From 4th to 12th century, European knowledge and study of arithmetic, geometry, and astronomy and music was limited mainly to Boethius' translation of some of the works of the ancient Greek master, such as Nicomachus and Euclid. All trades and calculation was made using the clumsy and inefficient Roman numerical system, and with an abacus based on the Greek and Roman models. By the 12th century, through Europe and particularly Italy was the beginning to trade with the East, and Eastern knowledge gradually began to spread to the West. Robert of the Chester translated Al-Khwarizmi important book of algebra into the Latin in 12th century, and the complete text of Euclid Elements was translated in various versions by Adelard of Bath, Hermann of Carinthia, and Gerard of the Cremona. The expansion of trade and commerce in general created growing particularly practical need for the mathematics, and arithmetic entered much more into the lives of the common people and was no longer limited to academic realm. So dito nga pumasok na yung mathematics sa mga normal na tao, kasi usually yung mathematics tinuturo lang ito dun sa mga pumapasok sa akademya, which is uso nga diba sa Roman and Greece. Pero ilan na yung nakapasok dito kasi mas nagtutuunan ng mga tao ng pansin yung pagtatrabaho or philosophy kaysa dito. The advent of printing press in the mid-15th century also had a huge impact. Numerous books and arithmetic were published for the purpose of teaching business people. Computational methods for their commercial needs and mathematics gradually became to acquire a more important position in education. So dahil nga dito, dahil nga sa mausbong pangangailangan ng mga tao sa commerce or trade, napilitan din yung mga traders or yung mga merchants na mas mag-aral pa ng arithmetic and mga numerical prepositions. So dahil nga dito, mas nag-improve pa yung kakayahan nila sa mathematics, which is nagagamit nila sa pakikipagkalakalan sa iba't ibang lugar. Halimbawa nga sa East Arabic, gano'n. So ito nga, tatalakayin naman natin kung sino yung unang great medieval mathematician. So, feeling ko lahat naman familiar dito kay Leonardo of Pisa, better known by the nickname of Fibonacci. Although best known for the so-called Fibonacci sequence of the number, perhaps his most important contribution to the European mathematics was his role in spreading the use of Hindu-Arabic numerical system. So yun nga yung kanina, explain ko nga kanina, yung Hindu-Arabic numerical system is yung 1 to 9 na number and the 0. Throughout Europe, early in the 13th century, which soon made the Roman numeral system obsolete and opened the way for the great advances in European mathematics. So dahil nga dito sa Arabic numerical system, mas nagamit ito ng mga taga Greece and Roman. So dahil nga dito kasi nga 'di ba, kagaya nga na explain ko kanina, parang hindi nga ganoon ka dependable or ganun ka-stable yung Roman numerical system. So, nung ginamit na nila yung Islamic numerical system, mas nag-improve yung pagkalakalan nila saka yung merch business nila. So, dito nga, may papakilala din ako sa inyong important, pero yun nga, hindi siya ganun kakilala and mostly underrated na mathematician na sumikat noong medieval period. The scholar of the 14th century was the Frenchman Nicole Oresme. He used a system of rectangular coordinate centuries before his countryman René Descartes popularized the idea, as well as perhaps the first time speed distance graph, also leading from his research into musicology. He was the first fractional exponent and also worked on the infinite series, being the first to prove the harmonic sequence series. The German scholar Regiomontanus was perhaps the most capable mathematician of the 15th century. His main contribution to mathematics being the area of trigonometry, he helped to separate trigonometry from the astronomy. And it was largely throughout these efforts that the trigonometry came to considered an independent branch of mathematics. His book of De Triangulus, in which he described much of the basic trigonometric knowledge which is now taught in high school and college, was the first great book of trigonometry to appear in the print. Mention should also be made of Nicholas of Cusa of Nicolaus Casarus, a 15th century German philosopher, mathematician, and astronomer, whose prescient ideas of the infinite and infinitesimal directly influenced later mathematicians like Gottfried Leibniz and George Cantor. He also held some distinctly non-standard intuitive ideas about the universe and the Earth's position in it, and about the elliptical orbits of the planets and related motion, which foreshadowed the later discoveries of Copernicus and Kepler. There was many reasons for the downfall of the Middle Ages, but the most crucial ones were the decline of the feudal system over the nations and states. In feudal society, everyone had a definite place and definite role, with the power resting in the hands of the local lords. instead of a central government. The lords or noble lost power after the Crusade when the European came into contact with the more advanced civilization of Byzantine Empire of the Muslim. So ito nga, dito na nga nagsimulang mag-decline yung mathematical, di lang pala mathematical, pati yung science and astronomy ng medieval period. Kasi mas pinagtuunan na nga nila ng pansin yung Holy Crusade, saka yung mga yung pag-establish ng government nila. Dito na nga pumasok yung Dark Age. Yun lang mga isa.
Mathematics during Renaissance period, 16th century. During this period, the most important figure is the Italian Franciscan friar Luca Pacioli, na mas kilala sa field of accounting dahil sa bookkeeping. So, meron siya mga libro na sinulat na nagpapatungkol sa arithmetic, geometry, and of course, bookkeeping. So, si Pacioli also, meron siyang book for the first time na nag-introduce ng symbols for plus and minus na printed or in a printed book. He also investigated the golden ratio sa libro niya noong 1509 entitled The Divine Proportion. He concluded na the message was from the Lord and it is a secret knowledge about the inner beauty of things. During the 16th and early 17th century, yung equals, multiplication, division, radical, decimals, and inequality symbols were gradually introduced and standardized. So, yung paggamit ng decimal fractions at decimal arithmetic ay attributed sa Flemish mathematician na si Simon Stevin noong late 16th century. Na-popularize yung decimal point notation noong early 17th century. In the Renaissance Italy, noong early 16th century, yung Bologna University ay nakilala dahil sa intense public mathematics competitions. Dahil sa competitions na yon, nakilala ang bata at self-taught na si Niccolò Fontana Tartaglia or Tartaglia, at pinakilala niya yung formula para ma-solve ang pinakaunang type at yung mga sumunod na iba't ibang types ng cubic equations. Dahil sa achievement niya na to, napukaw niya o nakuha niya yung atensyon ng best mathematicians sa China, India, at Islamic world. Sumunod sa yapak ng Tartaglia ang another Italian na si Lodovico Ferrari, kung saan gumawa siya ng similar method para naman ma-solve ang quartic equations. Yung dalawang method na ginawa ni Tartaglia at ni Ferrari ay pinublish ni Gerolamo Cardano, at sa matagal na pagtatalo sa publication o kung kanino ipapangalan, isa sa kanilang tatlo ang nag-demonstrate ng first uses ng complex numbers, combinations of real and imaginary numbers. Although, si Rafael Bombelli yung nag-explain kung ano ang imaginary numbers at kung paano sila gamitin. Si Tartaglia ang nag-produce ng iba pang important formulas and methods, and Cardano published perhaps the first systematic treatment of probability.
Now, let's proceed to the 17th century. This is the period where logarithms and Cartesian coordinates were introduced. So first, let us go on logarithms. Logarithms are used to assist the multiplication of quantities, or in its simplest form, it answers the question, how many of a number do we multiply to get another number? For instance, logarithm of 8 base 2, which means how many 2 should we multiply to get a product of 8? So the answer is 3, because 2 times 2 times 2 is equals to 8. Moving on, another mathematical discovery was introduced to the world: the Cartesian coordinates. Cartesian coordinates allow one to specify the location of a point in the plane or in three-dimensional space. For instance, we can see that the vertical line represents the y-axis and the horizontal line represents the x-axis. To sum up, the logarithms and Cartesian coordinates are the mathematical discoveries that happened during 17th century. Thank you.
During the 18th century, mathematicians embraced mathematics in general, calculus in particular, as a powerful set of analytic techniques used to describe the physical world. Advancement in mathematical methods fueled increasingly detailed descriptions and investigations of the world. Most of the well-known mathematicians of this century were French or connected to French Academy of Mathematicians, which undertook the task of producing a rigorous, self-consistent mathematical system that was closely related to natural phenomena. A set of mathematical techniques known as the calculus was developed during the last decades of the 17th century by English mathematician and physicist Sir Isaac Newton, and independently German mathematician Gottfried Wilhelm von Leibniz. Leibniz has more rigorous approach to the calculus, which set the scene for the mathematical work of the 18th century as compared to Newton. Leibniz greatly influenced various members of the Bernoulli in developing power and variety of applications of calculus. Calculus quickly found wide application even though its term of logic was not fully developed, and its use provided a number of new insights into the field of physics, astronomy, and mathematics. Calculus became an essential tool to describe a clockwork universe that supported Western theological concepts of unchanging, immutable God who ruled the universe through mechanistic laws. 18th century mathematics allowed mathematicians, scientists, and philosophers to have a deep and precise insights into the workings of the natural world. They relied more on scientific and mathematical descriptions or reasoning, which opposed the traditional theological descriptions of nature. 18th century mathematics emphasized a practical, engineering-like analysis of the material parts of physical systems like Newtonian kinematics. Most of the logarithm works, mathematical notations, terms, formula, theory, theorems, methods, and books in various branches of mathematics and science like geometry, calculus, trigonometry, algebra, field of mechanics, physics, statistics, and probability, during this time became a basis and foundation of mathematics of the next century that are still known and being applied today. Most of the well-known mathematicians of this century were French or connected to French Academy. Some of them were Jacob Bernoulli, Johann Bernoulli, and Leonhard Euler. In 1735, Euler solved an intransigent mathematical and logical problem known as the Seven Bridges of Königsberg's problem, which had perplexed scholars for many years, and this laid the foundation of graph theory and presaged the important mathematical idea of topology. The end result of these efforts provided the foundation for the construction and rise of pure mathematics during the 19th century.
Human beings from our earliest beginnings have searched for solutions to basic problems. As we journey through the rich and vibrant history of mathematics, we can see how ideas and creations grew out of our very human need to solve problems in our everyday lives. Now let us go down in history and discuss a very important chapter of the evolution of mathematics, the 19th century mathematics. The 19th century saw an unprecedented increase in the complexity of mathematical concepts. France and Germany, both caught up in the Age of Revolution, treated mathematics quite differently. England has also contributed a great deal of knowledge in mathematics history. Following the French Revolution, Napoleon Bonaparte, a French military and political leader, emphasized the practical usefulness of mathematics. His reforms and military ambitions gave French mathematics a big boost. At the beginning of the 19th century, Joseph Fourier's study of infinite sums, in which the terms are trigonometric functions, were another important advance in mathematical analysis. Fourier also contributed toward defining exactly what is meant by a function. In 1806, Jean-Robert Argand published his paper on how complex numbers could be represented on geometric diagrams and manipulated using trigonometry and vectors. The Frenchman Évariste Galois proved in the late 1820s that there is no general algebraic method for solving polynomial equations of any degree greater than 4. While the French focuses on the practical use of mathematics, Germany, on the other hand, took a rather different approach, supporting pure mathematics for its own sake, detached from the demands of state and military. It was in 19th century Germany that the young prodigy Carl Friedrich Gauss, also called Prince of Mathematics, received his education in the University of Göttingen. This young prodigy will soon turn out to be regarded as one of the three greatest mathematicians of all times, along with Archimedes and Newton. Gauss' ideas were 100 years ahead of their time and touched on many different parts of mathematical world, including geometry, number theory, calculus, algebra, and probability. The German Bernhard Riemann worked on a different kind of non-Euclidean geometry called elliptic geometry, as well as on a generalized theory of all the different types of geometry. Riemann soon took this even further, breaking away completely from all the limitations of 2- and 3-dimensional geometry and began to think in higher dimensions. His famous Riemann hypothesis, still unproven after 150 years, remains one of the world's great unsolved mathematical mysteries. British mathematics also saw something of a resurgence in the early and mid-19th century. Charles Babbage, in 19th century England, designed a machine that could automatically perform computations based on a program of instructions stored in cards or tape. His large difference engine, in 1823, was able to calculate logarithms and trigonometric functions. Although the machine was never actually built in his lifetime, but 200 years later, it worked perfectly according to his design and specifications. In mid-19th century, a British mathematician, George Poole, devised an algebra in which the operations were AND, OR, and NOT, which could be applied to the solution of logical problems and mathematical functions. He also described a binary system which used two objects. Boolean algebra was the starting point of modern mathematical logic and ultimately led to the development of computer science. The concept of numbers and algebra was further extended by the Irish mathematician William Hamilton in his 1843 theory of quaternions that can be used to transform one 3D vector into another. Englishman Arthur Cayley extended Hamilton's quaternions and developed octonions. Meanwhile, Bohemian priest Bernard Bolzano was one of the earliest mathematicians to begin instilling rigor into mathematical analysis, as well as giving the first purely analytic proof of both the fundamental theorem of algebra and the intermediate value theorem, and early consideration of sets. German mathematician Karl Weierstrass discovered the theoretical existence of continuous function having no derivative. He saw the need for a rigorous arithmetization of calculus from which all the basic concept of analysis could be derived. Weierstrass completely reformulated calculus in an even more rigorous fashion, leading to the development of mathematical analysis, a branch of pure mathematics largely concerned with the notion of limits. In an unusual occurrence in 1866, an unknown 16-year-old Italian, Niccolò Paganini, discovered the second smallest pair of amicable numbers, namely 1184 and 1210, which had been completely overlooked by some of the greatest mathematicians in history. In the later 19th century, George Cantor established the first foundations of set theory, which enabled the rigorous treatment of the notion of infinity, and which has since become the common language of nearly all mathematics. In the face of fierce resistance from most of his contemporaries and his own battle against mental illness, Cantor explored new mathematical world where there were many different infinities, some of which were larger than others. In 1881, the Englishman John Venn introduced his Venn diagram, which became useful and an ubiquitous tool in set theory. Hermann Minkowski, teacher of the young Albert Einstein, developed a branch of number theory called the geometry of numbers late in the 19th century as a geometrical method in multidimensional space for solving number theory problems involving complex concepts such as convex sets, lattice points, and vector space. Later in 1907, it was Minkowski who realized that the Einstein's 1905 special theory of relativity could be best understood in a four-dimensional space often referred to as Minkowski spacetime. Gottlob Frege's 1879 concept script broke new ground in the field of logic, including a rigorous treatment of the ideas of functions and variables. In his attempt to show that mathematics grows out of logic, he devised techniques that took him far beyond the logical traditions of Aristotle. He was the first to explicitly introduce the notion of variables in logical statements, as well as the notion of quantifiers, universals, and existentials. He extended Boole's propositional logic into a new predicate logic, and in doing so, set the stage for the radical advances of Giuseppe Peano, Buster Russell, and David Hilbert in the early 20th century. Henry Poincaré came to prominence in the latter part of the 19th century with at least a partial solution to the three-body problem, a deceptively simple problem which had stubbornly resisted resolution since the time of Newton over 200 years earlier. Poincaré was also an engineer and a polymath, and perhaps the last of the great mathematicians to adhere to the older conception of mathematics, which championed the faith in human intuition over rigor and formalism. He is sometimes called as the last universalist, as he was perhaps the last mathematician able to chide in almost all of the various aspects of what had become by now a huge, encyclopedic, and incredibly complex subject. Mathematics, also known as Queen of Science, permeates every area of our life. It helps to develop logical and critical thinking. It equips us with uniquely powerful ways to describe, analyze, and change the world. Through time, the mathematical explorations of every man and woman across the globe have given us fascinating lenses that help us mathematically view and make sense of the world. That's all for today. Thank you for listening.
The 20th century saw mathematics become a major profession. Every year,
Thousands of new PhDs in mathematics were awarded. Jobs were available in both teaching and industry. David Hilbert set a list of 23 unsolved problems in mathematics. These problems, spanning many areas of math, form a central focus for much of 20th century mathematics. So today, 10 have been solved, 10 are partially solved, and 2 are still open. The remaining 4 are too loosely formulated to be stated as solved or not. It might well be said that we live in an age of applied mathematics. Not only is there a distinct mathematical influence in our technology, but also in the arts. The dominating art is architecture, the most mathematical and, as Mr. Wilensky would have us believe, the fundamental art. Today, indirectly at least, pure mathematics is exerting a considerable effect on the development of our culture. This effect is reciprocal, and no one loses more than the mathematician by any attempt to deny this reciprocity. So how do we view our history nga ba? So we view the history of mathematics from our own position of understanding and sophistication. There can be no other way, but nevertheless, we have to try to appreciate the difference between our viewpoint and that of our mathematicians centuries ago.